Hi there, this is Bert Dixon here presenting on lesson 6.1, slope fields and differential equations. We've worked with a few differential equations already, and we were able to solve all the ones we've encountered so far, but there are differential equations that are very difficult to solve or in some cases impossible to solve, and slope fields give us a visual representation, a graphical representation of what the function might look like. Maybe it's not even a function, but what the graph of the equation might look like given the differential equation. So for this first example, we have a differential equation that is written in terms of x and y. And we can then use that to put slope indicators on the graph indicating that if the curve goes through a certain point, what the slope might be. For example, let's go ahead and just set up a table of values. And we'll chart the slope. And so if this curve happens to go through point 0, 0, we don't know if it does or not, but if it does go through the point 0, 0, its slope would be the x value plus the y value, so that is 0. So if a slope is 0 as the graph passes through 0, 0, then it would have a horizontal slope indicator. Now let's take a look. If the curve happens to go through the point 1, 0, then its slope would be 1 plus 0, which is 1. And a slope of 1 we know is a 45-degree line. And so we can put a slope indicator at the point 1, 0, indicating if the curve happens to go through that point, that's what the slope will be. Now we'll go ahead and do a series of other points. 2, 0, the slope would be 2. So I'm going to put a slope indicator that's a little bit steeper than the last one that I did. And then at 3, 0, the slope would be 3, so a little bit steeper yet. At 1, 1, the slope would be 2. At 0, 1, the slope would be 1. At negative 1, 0, the slope would be negative 1. So now we have slope indicators pointing the other direction. A slope of negative 1 is also at a 45-degree angle, but pointing in the negative direction. At negative 2, 0, the slope would be negative 2, so it's still a negative slope, but a little bit steeper, and so on. At negative 1, positive 1, the slope would be 0, and so on. So go ahead and pause your player, see if you can fill in the rest of the slope indicators on this grid that goes from negative 3 to positive 3 in the x direction and negative 3 to positive 3 in the y direction. Okay, with the slope field all filled in, now we have some understanding of what this graph might look like if it passes through any of these points. For example, if we were given information that this graph passes through the point 0, 1, 0, 1 is here, then the curve has to follow the slope indicators, meaning that as it passes through this point, it has to have the correct slope, which in this case is positive 1. And then we see that as we move to the right, the slopes get steeper and steeper and steeper. And then as we move to the left, it goes horizontal as it passes through this series of horizontal slope indicators. See, these are all horizontal slope indicators along here, so as it passes through there, it has to be horizontal. And then as it moves further to the left, it's going to take on a negative slope. And notice nowhere does my graph cross through a slope indicator. If it's crossing a slope indicator, then it has the wrong slope. We might also have a part of a graph that goes down through this negative section. It depends on the information that's given. And so this is the sketch of our slope field that we've generated by hand. Part B asks us to graph the slope field on our calculator. So I'm going to go ahead and pull up the calculator. If you were here when I installed the SlopeField program on your calculator, you have the program you need. We'll just go to Y1 and type in our equation. So it's going to be x plus y. Now this is different for different SlopeField programs. On the program that I've installed, you go ahead and type the equation right into y1. So we're going to have y1 equals x plus y, and we can get y using the alpha key. Okay, now we can press the program button and choose to execute the SlopeField program. So just press enter and enter again. And you'll see that this is generating a field of slope indicators similar to the one that I sketched on the screen. Now it has slope indicators drawn more often, but we still see going through the line y equals negative x, we see the horizontal slope indicators. We see the slope getting steeper and positive as we move to the upper right, and then becoming negative as we move further to the left and further down. So we see the same patterns on the calculator. Now let's go ahead and go on to part B, or part C rather. Sketch the solution curves satisfying the condition y of 0 equals 1. Now I've actually already done that. That was the first red curve that I drew. Y of 0 equals 1, so that means it's going through the point 0, 1. So I drew a red curve that goes through the point 0, 1. Now we can also draw one that goes through the point 0, 3. 0, 3, 1, 2, 3 would be up here. So to follow the slope indicators, it's going down through the point 0, 3 with a slope of 3, so it's pretty steep there. And then it has a slope of 1. And then remember, as I pass through the line y equals x, it has to go horizontal at that instant. And then it starts curving back upward to follow the slope indicators that are there. So that would be the solution curve that goes through the point 0, 3. We can also use SlopeFields to confirm what we do analytically. So let's take a look at a differential equation that we can solve, an initial value problem that we can solve, and then we can confirm this on our graphing calculator. Okay, solving the differential equation by hand. Actually, let's first just sketch the slope field. So sketch the slope field without knowing what the solution looks like. Notice that this differential equation gives us the slope in terms of x only. There's no y in this equation. We just have y, the derivative or the slope is equal to 2 times the x value plus 1. So if I'm at the point 0, 0, the slope is going to be 1. If I'm at an x value of 1, my slope is going to be 3. And not only is it 3 there, but at any point that has an x coordinate of 1, the slope is going to be 3. So I can continue moving up and down. And this will be true anytime you have a differential equation that is only in terms of x. You're going to have the same slope moving up and down because your x value is not changing. So the first one that I calculated at the origin had a slope of 1. Well, that's going to be true anytime the x coordinate is 0. So 0, 1, 0, 2, 0, 3, those all have a slope of 1. 0, negative 1, 0, negative 2, 0, negative 3. As long as x is 0, the slope is going to be 1. If x was 2, my slope would be 5, so we're getting very steep now. So these are all 5s. And then moving over into the negative direction, if x is negative 1, then we're going to have a slope of negative 2 plus 1 would be negative 1. So negative 1 all along this vertical line. If x was negative 2, we'd have a slope of negative 4 plus 1 is negative 3. And then negative 5. Okay, so there is our slope field. Now we can find the solution to the differential equation analytically. So it says y prime equals 2x plus 1. So y must be then the antiderivative of 2x plus 1. And that is x squared plus x plus a constant. And so if I choose different constants now, for example, one solution is just x squared plus x. That's a parabola that factors out to x times x plus 1, so it is going to cross the axis, the x-axis at 0 and at negative 1. And so if I sketch a parabola that crosses the x-axis at 0 and negative 1, that would look like that, and that looks consistent with our slope field. It's following the curvature that the slope field suggests it should follow. I'm not crossing any slope indicators. If I touch a slope indicator, my curve has the same slope as the slope indicator. Okay, another graph would be y equals x squared plus x. I can pick any constant I want, so this time I'm going to try plus 2. That's going to be the same parabola, but with a y-intercept of 2. So that's going to look like this. Okay, so we have a series of parabolas that are all general solutions of that differential equation. I do have an initial value for this problem. It is y of 0 equals 2, and so coming back to this equation, if I plug in 2 for y and 0 for x, I do get c equals 2, which is the last one that I just graphed. So the upper parabola is the one that is the solution. Okay, now we're going to see how this looks on the calculator. We're going to graph the, just like I did by hand here, I graphed the slope field and then I graphed the solution that I got, and we see that they fit pretty well. So if I repeat the same process on the graphing calculator, it would look like this. I go to y equals, I put in my differential equation, which in this case is 2x plus 1, and I'm not going to press graph, I'm going to press program, slope field, enter. It graphs the slope field, and then on the TI-83s and 84s, to superimpose a graph of our solution graph over this slope field, I go back to y equals, and I'm going to type my solution down here as y2. So our solution we got was x squared plus x plus 2. And now if I press graph, it keeps the slope field and graphs my curve, and we see that even though it's a little bit rough, the slope indicators there are a little bit hard to read. It does seem to follow the general curvature of the slope field. To do the same thing on a T89, after you've graphed your slope field in differential equation mode, then you can go to F6, draw, and draw function, and type in x squared plus x plus 2, and you'll see the same sort of graph with the graph of the parabola superimposed over top of the slope field. Eulers method is another process that we can use when we have a differential equation that is either difficult to solve or impossible to solve. We can still get some information about the function and predict values of the function even though we don't know what the original function looks like. So what you see here now on the screen is kind of a formula. It's a recursive process for finding points that should be moving along the curve. So we need to start with a point. We have to have a starting point and a derivative. And so our starting point is x sub 0, y sub 0. And then to get our next point, our next x value, would have x1 is equal to the previous x value plus the change in x. Okay, so there's our previous x value plus our change in x, and then our new y value is going to be our previous y value plus the derivative at the previous point. So remember, it's a differential equation, so we know the derivative. We plug in the previous point, x naught, y naught, and then multiply by delta x, and that gives us a new y value. And so what's happening is, the reason why Eulers method works is we have, let's say, a starting point on a, so we know the slope there, so we can draw part of the curve, and then we recalculate, we got a new point here, and now we recalculate the slope again, and then we got a new point, and we recalculate the slope again, and we got a new point, and then let's say the slope starts to flatten off a little bit, and a new point, and a new point. So we're calculating where the points of the graph should be based on what the slope is at the previous point. Okay, so I know that might be a little bit confusing right now. If we go through an example together, I think it'll make a little bit more sense. So using Eulers method with the differential equation dy dx equals 1 over x plus 1 and an initial value of y of 0 equals 2, we're going to move over in steps which are actually kind of large. Moving over 1/4 of a unit is a pretty big step, so our answer may not be great by the time we get to the end, but what we're going to do is we're going to take 4 steps to get from x equals 0 to x equals 1 so that we can approximate what the value of the function is at 1. We know the y value at 0 is 2. We want to know what the y value would be when x is 1. And so we're going to use 4 steps to get from 0 to 1. Okay, so we start with our initial condition, x of 0 equals 0, y sub 0 equals 2. And then following the recursive process, x1 would be our previous x value plus our change in x, so that's 0.25. And our new y value is our previous y value plus the slope calculated at the previous point. So our slope is 1 over x plus 1. Our previous point is 0, 0, so that's going to be 1 over 0 plus 1. So I'm taking this derivative and calculating it at the point 0, 0, or 0, 2 rather. So I'm evaluating the slope at the point 0, 2. Okay, so I'm evaluating the slope at the point 0, 2, and that is 1 over 0 plus 1, which is 1, and then multiplying times the change in x, which is 0.25. Okay, so that gives us our new y value of 2.25. Repeating that process again, I'll take my previous x value plus my change in x, that's now going to be 0.5. My new y value is my previous y value, 2.25, plus the slope at the previous point. Now remember, the previous point is 0.25, 2.25. That's my x1, y1. And so the slope at the previous point is now 1 over 0.25 plus 1 times our change in x, which is always 0.25 for this problem. And that gives us a new y value of 2.45. Go ahead and repeat that process 2 more times to get x3, y3, and x2, y2. Okay, completing the process, or replicating the same process over and over again. Now we have 0.5 plus 0.25 for x3, so that is 0.75. Our new y value is the previous y value, 2.45, plus the slope at the previous point. Now remember, our previous point is 0.5, 2.45. So our new slope is 1 over x plus 1, so that's 0.5 plus 1 times our change in x, and now we have 2.61667. One more step and we'll be there. X sub 4 would be 0.75 plus 0.25. That gets us to x equals 1, which is where we wanted to be. And now our y value there is 2.61667 plus the slope at the previous point, 1 over 0.75 plus 1 times our change in x, and now we have 2.7595. So we're saying now that using the differential equation and step sizes of 0.25, y of 1 should be approximately 2.7595. Now in part B, since this differential equation can be solved, we can see how close this approximation really is. So to solve the differential equation, we start with dy dx equals 1 over x plus 1. And so y is equal to the antiderivative of 1 over x plus 1 dx, which is natural log of x plus 1 plus c. And we know that the curve goes through the point 0, 2. So 2 equals natural log of 1 plus c, which means c equals 2. So our solution is y equals natural log of x plus 1 plus 2. And we want to know what is y of 1. Y of 1 is the natural log of 2 plus 2, which using your graphing calculator is about 2.69314. And we're comparing that is the exact answer compared to our approximation 2.7595. Not a great approximation, but remember we only took 4 small steps. We could improve our approximation if we had taken 10 steps with a delta x of 0.1, then we would have gotten much better results. Or you could take 100 steps with a delta x of 0.01, and we'd have, I'm sure, very good results. And so smaller step sizes are great, but that also means you need to repeat Eulers Method, the process, many more times. Instead of doing it 4 times like we did here with a step size of 0.1, you'd have to start with x0, y0, and keep going until you got to x sub 10, y sub 10. And so that would take 10 steps for you to get an approximation using a delta x of 0.1. I'm going to go ahead and stop right there. Example 4, we can do that one together in class with a spreadsheet. So that completes today's lesson on 6.1.